In this video, we're going to cover stability, and stability can be from three different ways. Our first way is from concurrent reactions, which literally mean they're like all pointing at each other. We can have parallel reactions where they're all going in the same direction as each other, or we can just simply have not enough reactions using our equations. Now it can be for the beam frame one, or it can be for a truss. So again, remember, if you don't have enough reactions, then your beam, frame, or truss kind of just falls apart. So that's one way it can be unstable. But if you are determinant, you can also be unstable if you also have one or two. That's also going on for our stability problem here. So even if you're determinant, if you have concurrent reactions, or if your determinant have parallel reactions, your truss is still not stable, or your beam or frame is still not stable. So let's have a look at what that can be. So this, we're just going to go ahead, it's a truss, so let's go ahead and figure out the number of bars. 1, 2, 3, 4, 5, 6, 7. So we technically have 7 bars. The number of external reactions is 1, 2, and 3. Right, so 1, 2, and 3. And then we have a force P here, and that P is just going to help us really look at the concepts. So again, we have 7 bars plus we had 3 external reactions, and that compares to how many joints? 1, 2, 3, 4, 5 joints. Remember, it's 2 times J, so 2 times 5. So 7 plus 3 is 10, and 2 times 5 is 10, so this is determinant. Right, so this is a determinant truss, but that does not make it a stable determinant truss. So this might not be very obvious at first, but we have concurrent reactions here. And you see how they're pointing toward each other. So what is actually making this unstable? Well, let's just find out how this works. If you were to sum the moments about A and set it equal to 0, and we're just going to call this point A over here. If we sum the moments about that pin and set it equal to 0, taking counterclockwise to be positive, and P is an actual force of actual value, then P is here, and you know, whatever, he's negative P, right, because he's going to be going this way around. So he's going to be negative times whatever the distance that he is vertically. But the roller's reaction is also in line with A, so there's no other reactions. So how can this equation be true if P is an actual value? So if that's the case, this is not stable, right? We always say that if it all sums together and it doesn't equal to 0, that your structure is moving. Well, moving is instability. So in this case, your structure is moving since it did not equate to 0. Therefore, it is not a stable truss. So that's how concurrent reactions fail. And here we're going to have the same truss, same exact thing, the only difference being that we have our 3, still 3, right? Still 1, 2, 3, still 3 reactions. They're just all parallel. So now you apply force P, and force P is horizontal. And if we sum the forces in the x direction and set it equal to 0, well, the only thing we have is P, but remember, P is an actual force. So if we have actual force in 0, and that's not the case, then this isn't true, and our truss is on the move, and that again is unstable. So it's not necessarily about the fact that you didn't have enough. Obviously, not having enough reactions does cause it to be unstable, as it can just fall apart. But those parallel reactions and those concurrent reactions are there to show you that even though you had enough reactions and it was a determinant structure, it's on the move, and that's not stable.